This is Classical Physics 2, and it's a calculus-based physics class, and we're in Chapter 22, Working Problems. We're going to start with number 4. You have noticed that I only work the even problems because that answer doesn't occur in the back of the book, and therefore you can't check to see if my answer is right or wrong. Number 4, a uniform field E is parallel to the axis of a hollow hemisphere of radius r. Okay, so now the issue is, can I draw such a thing? And we'll see whether or not we can or not. So I've got, oh, isn't that lovely? So I've got some uniform magnetic field E going into it. Okay, so that looks good. And the issue is, what is the electric flux through the hemispherical surface? So I look at that and I say, well, the flux through the base of this object is the same as through the hemispherical surface of the object. So flux is what? E cross the area. And because of that, I can just use the base of the hemisphere. So that's pi r squared. So that'd be pi r squared E. So that would be the flux through the hemispherical surface. So even though I'm not considering that surface at all, I'm just considering the surface of that circle. Whatever flux goes in the circle has to come out the hemisphere. Therefore, that would be the answer to the A problem. Well, that was way too easy. Problem B, what happens if the flux comes in a different way? So we'll have our hemispherical surface sitting like this. Okay, so there's my hemispherical surface, and I have flux. I have an electric field going that way like that, and the issue is, what is the result? In other words, what is the flux if E is perpendicular to the axis? So the axis is like that, and my E is perpendicular to the axis. Okay, well, in this particular case, anything that comes in comes out. And because of that, the flux is going to be 0. In the first case, the flux that passes the surface doesn't come back. In the second case, the flux that passes into the surface leaves the surface. Therefore, the flux is 0 through that surface. That seems kind of weird, but that's the way it is. Number 8. A ring of charge with a uniform charge density is completely enclosed by a hollow donut shape. All right, well, let's see if we can draw that. So here's a ring, and it has some flux density, and it is enclosed by some donut shape thingy. All right, so that's being the case. An exact copy of the ring is completely enclosed in the hollow surface. What is the ratio of the flux out of the donut shape to that out of the surface? An exact copy of the ring is completely enclosed in a hollow sphere. Okay, now we're going to have to figure that out. So I've got the ring again, but this time it's not enclosed in a donut. It is enclosed in a sphere. Okay, so those are my two cases. I have a donut and I have a sphere. What's the ratio of the flux out of the donut to that of out of the sphere? Well, because the Q is the same in both cases, then the flux has to be the same in both cases, and the flux ratio has to be 1:1. All right, well, that's two simple ones in a row. I imagine that the next one won't be. I'm going to do number 18 next. A solid metal sphere of radius 3 meters. Solid metal sphere. Okay, so I got a radius 3 meters. Okay, carries a total charge minus microcoulombs. All right. What is the magnitude of the electric field at a distance from the center of the sphere at 0.25 meters, 2.9 meters, 3 meters, 8 meters? How would the answer be different if I have a thin shell or if I had a solid non-conducting uniform shell? All right, well, I read the whole problem. So the first issue, A, what is the magnitude of the electric field at a distance 1/4 meter from the center? And that's going to be 0. Because I'm at equal charges around there, and inside the sphere I'm not going to see any electric field. So my electric field would be 0. B, what is this? This is a solid guy. Yeah, that'd still be the case. Inside a solid guy, the electric field is going to be 0. B, we're still inside of the field. I found the distance 2.9 meters away, so my electric field is still going to be 0 in both of those cases. C, I'm going to be 3.1 meters away, and we find that we have an equation now, and E is going to equal 1/4 pi epsilon naught Q over R squared. And let's see if I can show you where that came from. And that's equation, there's no equation number for it, but it's on page 595, around 3/4 of the way down the page. If R is greater than R naught, then that means I'm outside the sphere, and I use that equation. Okay, well, back to where we were. So that would be K, 8.9, 88, 10 to the 9th, newtons meters squared per coulomb squared. 5.5 times 10 to the minus 6 coulombs divided by the radius, 3.1 meters squared, and I end up with an electric field of 5,140 newtons per coulomb. And I look at the D answer, and I'm going to use the same exact formula, and I'm going to say that E is 1 over 4 pi epsilon naught Q divided by absolute value of Q divided by R squared, and I end up putting in my calculator 8.98 times 10 to the minus 10 to the ninth. So 1 over 4 pi epsilon naught is my K. 5.5 times 10 to the minus 6 divided by 8 meters squared, and I end up with 772 newtons per coulomb. Okay, now we're going to look at the E part of the answer. 18E, it's a thin shell. Okay, being a thin metal shell or being a solid object makes no difference, so that there's no difference because what happens is on the solid, the charge is all going to be on the outside. In a thin metal shell, the charge is all going to be on the outside. So it makes no difference at all whether I'm solid or not. Whether or not I'm a solid guy or I'm a thin piece of conducting material. A solid non-conductor uniformly charged throughout. All right. Then at this point it's going to make a difference. So if I look at exercise 22-4, we find that if I'm inside the non-conducting sphere, I have an equation that's E is going to be 1 over 4 pi epsilon naught Q divided by R naught cubed over R naught cubed R. And if I'm outside, then my E is going to be my 1 over 4 pi epsilon naught Q over R squared, and that's gonna be the difference. So now we're going to redo part A, where R is equal to 1/4 of a meter, and we end up with E being 8.988 10 to the 9th newtons meter squared per coulomb. Times 5.5 10 to the minus 6 coulombs divided by 3 meters squared times 1/4 meter. And we end up, before we had a 0, and now we have 458 newtons per coulomb. Redoing the B guy with, so my E, when R is going to be 2.90 meters, I'm going to end up with 5,310 newtons per coulomb. Redoing the C part, I'm going to end up with the same answer. So redoing the C part, I have the same answer as before, 5,140 newtons per coulomb, and redoing the D part, I end up with the same answer as I had before, of 772 newtons per coulomb. Okay, now we're going to move to number 24. And I have two flat plates separated by a distance that is very small compared to their height and their width. The conductors are given equal but opposite uniform charges, densities, well, plus or minus rho. Is that a rho? Ignoring the edge effect, ignore the edge effect and use Gauss's law to show that all the points far from the edge, the electronic field is going to be rho divided by, that's not a rho, sigma. Sigma divided by epsilon naught. And then there's a B and a C part. Okay, so we've got the two metal plates. One is charged, and they've got some thickness associated with them. One is charged plus sigma, the other guy has a charge minus sigma. The plus charges are all going to be on the outside of the plate, on the near closest to the other guy, and the negative charges are all going to be drawn to the outside of the plate closest to the plus guys. All right, so that's just a matter of opinion. They're going to move to the edges of the plate, and no charges are going to be on the outside of the plate. And these two guys are perpendicular to each other. Okay, so to find the field between the two plates, we're going to have a Gaussian cylinder that's perpendicular to the plates. All right. So now we're going to have something perpendicular to the plate sitting there. Where the area A on the end of the cylinder, and so we have some area A sitting right there. So if we do a surface integral of the field across the surface area, then we're going to have surface integral of the right side of the ends. Surface area of the ends plus the surface area, surface integral of the sides Alright. And the sides are in parallel with the field, so that's going to be 0. So this has to be the surface area of just the right side. Could be just the left side. Cross the other guy. And that's going to be the charge enclosed divided by epsilon naught. Okay, so I haven't not sure I like my picture, but that's what we have. So the area, the electric field between the two guys, okay, so I haven't not sure I like my picture, but that's what we have. So the area, the electric field between the two guys, so the electric field between the two guys, 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 the electric field between the between the two surfaces times the area is going to equal sigma area epsilon naught, which implies the field between is going to be sigma divided by epsilon naught. And was that what we were supposed to do? Yes, we're supposed to show that it was sigma. Now we want to do the B part. Okay, and now we're going to come back and redraw my cylinder because I don't like my cylinder. Okay, so we're going to redraw my cylinder to look like that. Okay, now there's the right side of the cylinder. Here's my charge that's enclosed, and that charge enclosed has to get out that way. And it's not going to go this way, it's not going to go that way, and it can't go the other way because I have negative on this side and positive on that side. So the field lines of flux have to go through the right hand side. Okay, so I like my drawing and I like my answer. Now I'm going to do it again, and that outside the plates on either side of the field is 0. Okay, so now the B part of the answer, here's one of my plates. It's but all of its charge is sitting over here, and because all the electric field is going that way towards the negative charges that are on the other plate, if I put a cylinder here, then I see there is no lines of flux going through it, and therefore I have there's no charge enclosed, therefore I can't have any electric field leaving. And so the electric field outside is going to equal 0. Okay, number 32. Suppose that at the center of a cavity inside the shell Q of charge Q, figure 2211, there is a point charge Q, which is not equal to plus or minus big Q. Determine the electric field for A between a radius between R and R naught, and B greater than R. And what would your answers be if Q were equal to Q, or if Q were equal to minus Q? Okay, so the first thing we have to do is find figure 2211. Okay, so I'm looking at 2211, and got something that looks like that, and I have an R naught, which looks like that. I've got an R, going out to area 2, and then for some reason or other I have another R that is labeled R, also going out to area 1. And now what I need to do, okay, so that's what I have. And 32, suppose that that's the case, but there's a point charge Q. And suppose the center has a point charge Q. So I got in the center of this thing, I got some little q. And on the outside, I've got some capital Q. Okay, so that's what I've got. And so now the issue is determine the electric field for 0 to R. So I want, okay, so I'm going to find the electric field inside. So I go from 0 less than R less than R naught. Okay, so that's what I'm looking for. And I go back to example 22.3. And the electric field is going to have to be, when R is less than R naught, is going to have to be little q, the guy in the middle, times 4 pi epsilon naught R squared. Because when I'm inside the sphere, there is going to be no electric field caused by what's on the outside of the sphere. But when I'm inside the sphere and there's a little q sitting in the center there, I'm going to see that effect. The guys on the outside are canceling each other out. They're not doing anything. Okay, so that's my A answer. Now for my B answer. B answer, I want E for R greater than, that doesn't look like a greater than sign, does it? R greater than R naught. Well, in that case, I would have the Q again, 4 pi epsilon naught over R squared, but I'd also have the capital Q guy divided by 4 pi epsilon naught R squared. And I could probably do something clever like add those together. Q plus Q over 4 pi epsilon naught R squared. Okay, so that would be my B answer. My C answer, if Q were equal to Q. Okay, so they're both equal to each other. So now my E at R less than R naught is going to be the same answer for before. My little q can be a big Q now. 4 pi epsilon naught R squared. And if E is going to be for R greater than R naught, then I add those two together, 2Q over 4 pi epsilon naught R squared. And then there's the D part of the answer. D part of the answer, we have Q equal to minus big Q. Okay, so E is going to equal E at R less than R naught. We're going to have minus Q over 4 pi epsilon naught R squared. And when R is greater than R naught, we're going to end up with 0 because the two are going to cancel each other out. Okay, now we're going to move on to number 44. Suppose the charge density, the density of charge between R1 and R2 of a hollow sphere, figure 2232, varies. Determine the electric field as a function of R in several places, and then plot it as well. Okay, so the first thing we need to do is find figure 2032. 2030. I got 2022, but I need 2032. Okay, so I got something that looks like that. I've got a positive charge Q uniformly distributed in the solid. I've got an R1 and I've got an R0. Okay, so that's my figure 2232. Okay, so that's the case. And I know that the density of the charge is density naught R1 divided by R. Now that's interesting. Oh yeah, R1 divided by R wherever I happen to be. Right. Alright, so that's going to be the case. Alright, so number 40, the A part. In the A part, if I'm between 0 and R1, so that's, I'm inside the hollow portion, well, that has to be 0 because the electric field is going to be we need more room here. The surface integral of the electric field across whatever the area is has to equal the charge enclosed divided by epsilon naught. The charge enclosed is 0, so this is 0. If this is 0 and the area is not 0, then the electric field has to be 0. So the A, and we've already done that before. We've shown that in other places as well. A, B. Now we're going to be R1 is going to be between R is going to be between R1 and R0. So now I'm inside the sphere. So I'm going to look out. I'm going to consider the volume of the charge density. And I'm going to multiply it by that. The volume of the charge enclosed Okay, so that's what I'm going to look at, and we're going to use our rho is equal to rho naught R1 divided by R, and we're going to follow our example 22-5, and we're going to find that the charge enclosed is the integral to rho density, change in volume. So that'd be integral R1 to R, rho 0, R1 divided by R1 prime, 4 pi R prime squared, R prime, not R1 prime, dr prime. And only a real math major would like that. And that's going to be 4 pi R1 rho naught integral R1 to R of R prime dr prime, which is going to be 2 pi R1 rho naught times R squared minus R1 squared. Okay, so this would be R squared over 2, R1 squared over 2, but that over 2 got divided into the 4. That's why I have that 2 out there. All right, so E, which is what we're looking for, is the enclosed charge divided by 4 pi epsilon naught R squared. Okay, and I already have the enclosed charge, so that'd be 2 pi R1 rho naught R squared minus R1 squared divided by 4 pi epsilon naught R squared. And we end up with a final answer of rho naught R1 R squared minus R1 squared divided by 2 epsilon naught R squared. All right, so that would be the equation of the electric field inside the material. And now we have to do the C part. And the C part would be for R greater than R naught. So I'm outside of the sphere now. The amount enclosed is integral of the density d volume, integral R1 to R0 rho naught R1 divided by R prime 4 pi R prime squared dr prime. And that's going to equal 2 pi R1 rho naught R0 squared minus R1 squared. All right. So that's the amount enclosed. E is the charge enclosed divided by 4 pi epsilon naught R squared, which is going to leave me with rho naught R1 R0 squared minus R1 squared divided by 2 epsilon naught R squared. Okay, now we're going to do a plot of the equations that we have. Okay, so we'll look at this, and we'll this is going to be 1/2 and 1 and 1/2 and 2, and the x-axis is going to be R divided by R naught. Okay, and on the other side we're going to have a graph of E divided by E naught. Okay, so that's going to max out at 1, and they might have a 1/2, a 3/4, and a 1/4 just to look at things. So I'm going to start off at 0, and I'm going to go to 0 until I reach the first shell. I'm going to max out at 1, and I'm going to grow. How am I going to grow that? So there's the 0 part. Okay, so R squared here, R squared there, R1 minus R, that's a constant. So this is going to be some number divided by R2's R squared. Okay, so that's going to be something like that. And then once I get to the outside, I'm dividing by r squared as I get bigger. So this is going to go and drop down. And at 2, we're going to be at a quarter. Okay, that looks good for a graph. Alright, so that ends problems that I'm solving in chapter 22.